Okay, so the chapter is magnets and materials, right? Okay, so we start with, okay, so you don't need to remember ferromagnetic materials or magnetic materials, something like that. What you need to remember is that some materials can show magnetic properties and some of them cannot, right? The ones that do show that are known as magnetic materials, and and those substances or elements that cannot show magnetic behavior are known as non-magnetic. So it should be a part of your memory that brass, copper, wood, and plastics, no matter what you do with them, they will not become a magnet. Then we have ferromagnetic materials or magnetic materials such as cobalt, nickel, and steel, who under special conditions may exhibit magnetic properties. Or, of course, we make permanent magnets or magnets out of steel because it's a relatively easier metal that is available. So we make magnets out of them. And if you suspend, how would we identify whether a stick of bar of, let's say, steel, iron, or any other material that you are holding right now is itself a magnet or not? So this is the experiment that we conduct, right? We will freely suspend this magnet in air and wait for it to align itself according to the magnetic field of the Earth. So it will act like a compass or a large compass, right? Do we understand this point? So basically what we're trying to do is we're trying to just verify whether this will align itself according to the magnetic field or not. And they generally do. If the magnet is strong, they will generally respond to the magnetic field of the Earth. Okay, so now let's try to figure out. Are you speaking right now? Right.
No, no.
Okay, so keep the mic. I would respect that. Okay, so uh, the way we identify magnets is important for this chapter. Is that, for example, if we hadn't known that this sub object that we're hanging on the rod right now is a magnet or not, let's say we're blind to that, we don't know what it is, right? So how are we going to find out whether this is a magnet or not? So we will bring in a known magnet and perform a very simple experiment. You see, magnets can attract from their south pole and from their north pole towards iron. They can attract iron, irrespective if you bring south pole or the north pole. It doesn't matter. For a magnetic material, it would not matter for a magnet to attract it from any pole there is. So if we don't know what this substance is or this object is, what we're going to do, we're going to check it with both poles with a known magnet. So for example, if I bring in the south pole and it gets attracted, that does not prove anything. So attraction does not prove that this material is a magnet or a magnetic material, right? What proves that this will be a magnet is the repulsion. Because if it is being attracted by South Pole and North Pole both at the same time, that would simply mean that this material itself is, let's say, iron or steel or cobalt or nickel. It can show magnetic properties, but itself is not a magnet right now. That is why it is being attracted by these poles all the times, right? So be that South Pole, be that North Pole, it will be attracted from both of them. So it doesn't prove anything. So attraction is not the guarantee, or is not the absolute guarantee, or not the final word in this experiment to confirm whether this will be a magnet or not. So, what confirms that this is a magnet itself or not is the repulsion. Because if it would be a magnet, not a magnetic material, then it would also have a pole. So, if you tested with the south pole at the beginning and it attracted it, now you bring in this north pole and see for the same end of the bar, does it attract or repel? If it repels on any orientation, that will give us the 100% guarantee that the material that we're testing right now, or the object that we're testing right now, itself is also a magnet. So the identification of magnetism requires repulsion. This is the underlying thing that we're looking for. Okay, so let's move. These are the notes that he's going to discuss with you, right? So please confirm this, that repulsion is the only test to confirm that an object is a magnet. Otherwise, we will totally blind. We can only say that this is a magnetic material, not a magnet itself, right? Okay. So By this time, we know that North Pole and South Pole attract each other, right? For example, we know up to this point that same poles will repel each other. They will repel each other. Similarly, South and South will repel each other. But unlike poles, for example, North and South, they will attract each other, right? This is common knowledge. Okay, so the next topic that we have is induced magnetism. Now, this mechanism actually helps us understand that why and how does a magnet attract another magnetic material. Attracting another magnet, that would be the last part of this topic. But right now, what we're trying to understand is that how is that possible that, for example, a magnet attracts a piece of iron or a piece of cobalt or a piece of nickel? Why would it do that? Or how would it do that? You see, for example, this is a known magnet. Let's say this is a magnet, and I bring it close to iron. I know that iron will be attracted to it, but what's actually happening with the iron? You see, the magnetic field of this south pole is actually overlapping, or you can say it's actually trying to cross over to or through the iron piece as well. And as a result of that, it will introduce a north pole at this location. This introduction of an opposite pole is known as induced magnetism. But now let's try to see what's actually happening at the particle level with the iron or with magnet. What's actually happening at the particle level that actually enables this behavior? So for that we need to understand the term magnetic dipoles, right? So we need to understand magnetic dipoles and we also call them magnetic domains. So basically what he says is that a piece of iron, for example, a piece of magnet, let me show that to you. Okay, so this is what we are talking about. So what he says is that a piece of magnet or a magnetic material or anything like that, especially magnet, would have smaller magnets or it would be actually made up of smaller magnets which are called magnetic domains or magnetic dipoles, right? So that tiny magnet represents a particle of a larger magnet. So if all of them are disorientated or they are not aligned in a single direction, as I can see over here, that all of them are pointing randomly in all directions. So the result of all of this would be that there is no magnetism. For this to become a magnet, all the atomic magnets or magnetic dipoles or magnetic domains need to be aligned in a single direction. In a single direction. When that happens, this will eventually become a magnet. So for the dipole or the domain, the head represents the North Pole and the tail represents the South Pole, right? So at the particle level, many or a magnet is made out of many dipoles. When all of them are pointing in a single direction, collectively we say that this will become a magnet now, right? So if we go back to the same idea that I gave you before, this one, so what's actually happening is that when these lines, when they cross another material, they try to align the domains of that material. So basically over here, the domains are trying to align themselves for, of course, the part of the iron that is actually exposed to the magnetic field. And in this attempt, or in process of this, this end ends up getting the opposite pole, and as a result gets attracted to the south pole, right? So I'm taking a pause at this. So moving on, let's try to understand this question. This is interesting in terms of an MCQ. So what he does is that he takes a magnet and could be performed with the south pole as well. We are not concerned with the poles right now. We're concerned with the main idea, the idea that leads to the confirmation of induction. So let's say I place a barrier between the north pole that is made out of wood and I place another barrier with the iron that is made out of, let's say, iron. And what I'm trying to prevent is that I have paper clips on the other side that are made out of iron, and I know that they will be attracted to it. These are paper clips placed in a bowl, right? Could be many paper clips, we're not concerned with that. Okay, so in which case do you think the paper clips would be attracted, and in which case the paper clips would not be attracted? The answer is quite opposite to the intuition. Uh, in the case of iron, they will not be attracted, and for the case of wood, they will be attracted. Now let's discuss the reason for that. You see, when the magnetic field lines are actually passing through, sorry, when they're trying to pass through the air like this, they encounter iron. Now, iron is a softer material, you can say, in terms of magnetic field lines. Iron will allow the magnetic field lines to pass through it with lesser resistance to the magnetic field lines as compared to simple air. So let's summarize this. Magnetic field lines prefer to pass through iron rather than air. The concept is known as permeability, and I believe so. It's permeability or permittivity, but you will find that in higher levels education when you'll have to identify the magnetic field lines and its respective calculations. So, not even I haven't seen this in A levels as well. So, the idea of permeability or permittivity that will exist, but not with magnetism. So, it only says that in terms of electrical resistance, we actually thought that how difficult will it be for the electrons to flow over here. We take that concept as how difficult it is for the magnetic field lines to move or to flow through air. So the magnetic field lines prefer to pass through iron rather than air. So the magnetic field lines will actually pass through iron and not even reach the paper clips. So if they're not reaching the paper clips, how is the magnet going to attract them? But in the case of wood, since wood is not a magnetic material and it's as good as nothing, right? So even if there was something or even if there isn't, it doesn't matter. So the magnetic field lines successfully do reach the paper clips and cause magnetic induction. So if this is the North Pole, they will observe a South Pole at this location and end up being attracted towards the lower side of the wood. This is what the experiment he is conducting right now. That is what is being done right now. Let me show that to you over here. So through wood, iron nails do get attracted. But if it had been a piece of, let's say, iron or steel, they would not have been attracted because the magnetic field lines would have passed through the iron, right? So the process that we are representing over here, the introduction of the opposite pole, is known as magnetic induction. This is what he will say at this point. You'll find this in the slides as well, right? Okay. So this magnetic domains, we have discussed that as well. They need to be aligned in one direction. So this is what a magnetic field looks like. So what we have over here are iron filings. This is just iron powder that is sprinkled around the magnet to see what the magnetic field actually looks like around the magnet, right? And if you wanted to find out the direction of magnetic field, always remember for throughout the end of this chapter, magnetism, electromagnetism, electromagnetic induction, unless or until we start with radioactivity, till the end of this chapter, we will always use a compass to find the direction of magnetic field, which is also important. Do we understand this point? Right? So what is the meaning of direction of magnetic field? So if I place the compass at this place and compass at this point, and of course at multiple locations, how will the needle of the compass look like to me? So when we answer this question or trying to find out the answer for this, what we land is, or what we find is that, for example, if this is the North Pole and this is the South Pole, so for the North Pole, we have the needle pointing away from this. Why? Because inside the compass, the needle part represents the North Pole and the tail part represents the South Pole. So when we place it close to the North Pole, the needle head is also north, the North Pole is also north, they repel each other, so the needle ends up pointing away from it. Similarly, if we place it closer to the South Pole, the needle ends up pointing towards the South Pole. Why? because the head is the north and the tail is the south. So it goes both ways, that the south pole is repelling the south pole, so it ends up on the other side, and south pole is attracting the north pole, so it is on the closer side. So that is how we figure out the direction of magnetic field. And in the incoming diagrams, when we see the direction of arrows around the magnetic or around the magnet, they have been drawn looking at the compass itself. So these arrows or this diagram has been drawn or has been made using a compass. Otherwise, we could not have pointed out the arrows. Do you understand this point? Right? So what we have done is we have placed a compass at multiple locations. Similarly, where we find the arrow, and we've just plainly looked at the direction of the of the needle, right? So if I placed a compass at this point, it would look like this. If I placed a compass at this point, this is what it would look like. So compass at multiple locations between these magnets, and I can see where the arrow is going to point. Now, there is a rule for that, right? So what the rule is that for the North Pole, the magnetic field lines are considered to be pointing outwards. Why? Because if I place a compass close to it, the needle points away from it. So looking at the direction of the needle, this is what we've concluded. Of course, not a very scientific method, but this is what scientists and engineers have accepted worldwide. This is how we're going to categorize it. So let's say if this is the South Pole, the outlook of the magnetic field is the same, but the direction is opposite. So for South Pole, the magnetic field lines point inwards, and for the North Pole, they point outwards. And of course, we have found this by looking at the compass only, right? So now, if we compare this at this location, it makes more sense. How? If I look at it from the perspective of the North Pole, they are pointing outwards or they are pointing away from the North Pole. But if I look at it from the perspective of the South Pole, I see that they're pointing inwards. So if I combine the effect of both, the resultant effect is that the combined direction is in this direction. Do we understand this idea? Right? So the combined effect is what we have shown at this point. So this is what we're looking at. Okay. So this is the magnetic field pattern. Now this is also part of our course. Magnetic field pattern for when the poles are unlike. Let's say one is north, south, south or north, doesn't matter. This is what the field pattern is going to look like. And this is directly a question's answer for an MCQ. And even if he asks the directions from you or the magnetic field pattern from you, this is what you're going to draw, right? Okay, so let's move to the next part. This is the magnetic field line pattern if we find that the magnetic fields or the magnets are repelling each other. Do we understand this idea, right? And the region X is special in terms of understanding. The region X is a region where there is no magnetic field. And one more thing that we would like to understand at this point is that notice that for the North Pole, every time we draw the arrows, it is going to point outwards or away from the poles. If this had been a diagram between the South Pole and the South Pole, the direction or the pattern of the fields would be the same, with only one exception. And that exception would be that this time around they will be pointing inwards as opposed to outwards for the North Pole. Do we understand that? So you can see that for North Pole, for both North Poles, the field direction is outwards. For both South Pole, the field direction will be inwards, but it will be exactly going to look like this, with a region at the center where there is no magnetic field. So if you placed a compass at this point, it will not be pointing towards any direction, particularly. Right? Okay. So these are again some questions or some answers to the MCQ questions. This is much easier to understand, but this one is a bit complicated. We can see that if you swap if you swap the positions of the magnet, so north is in front of south and south is in front of north, so what is it going to look like? This is what the magnetic field is going to look like. And to tell you another point about this is that when you want to store magnets, for example, laboratories, in school laboratories, if we know that the magnets are not going to be used for the, let's say, next 6 months because the schools are closing down or the lab is going to be renovated or whatever that is, we actually store the magnets in this configuration. So this is a magnet storing technique. opposing magnets or opposing poles stacked onto one another. So let's say if I had to stack another magnet, that would be south and north. If I had to stack another magnet, that would be south and north in this way. Do we see how they are opposing the opposing poles are being placed on top of one another? So that is how we're going to store the magnets so that the magnetic field lines can continuously flow through them and strengthen each other, right? So that actually helps maintain magnetism or store magnetism and it doesn't get lost over time. Okay. So this is the magnetic field line of the Earth, right? Uh, this is what we are using the compass for. This is how we're using the compass. Or actually, this is what we're trying to locate. We're trying to use a smaller compass so that we can find ourselves along the direction of the magnetic field lines of the Earth. And that is how we try to navigate through it. So this magnetic shielding concept has been removed from your course. We don't need to study that again. But I have taught you a bit about that. That if you remember that I just discussed an MCQ with you that magnetic field lines prefer to pass through iron and steel rather than air. So whatever is placed on this side of the magnet will be effectively shielded from the magnetic effects. We use these devices or we use these materials when let's say we are getting an MRI scan. That is a magnet, a very large magnet that is trying to resonate with the hydrogen atoms or provide energy with the hydrogen atoms. So what we do is if we want to protect the people around it or the people who are actually working on the machine, we will enclose this machine in an iron or steel ring so that magnetic field lines would not cross out of the system, right? So, and similarly, the hard drives that we have for our laptops, you may notice that they have a very solid case installed on them. That is generally made out of a material that can provide magnetic shielding so that any external magnet, because hard drives previously, now we have SSDs, but previously hard drives were made out of magnetic materials, and they would run the risk of, you can say, running out of, let's say, running into errors because of an external magnetic field, right? Do you understand this point? Okay. All right. So you can study about that. This is not related to your syllabus anymore directly. If you want to read this, if you want to read about this, that's your choice. So then we have how to draw the magnetic field, and this is what we discussed just now, that we use the compass to draw the magnetic field lines around the magnet. And even let's say, for the sake of example, let's say we didn't know that what pole is this one and which pole is this one. We're trying to remember that the red one is north and the blue one is south. Let's say we don't know what that is. So even in this case, if I bring in a compass close to this point and I see that it is pointing towards that pole, that would mean that this is south. And if I bring a compass at this point, it is pointing away from it, then I would generally mean, or I would understand that this is north. So just by looking at the direction of the compass arrows, I can predict that this is south, pointing inwards, and this is north, pointing away from the pole, like this one, right? So this is how we can identify for those parts or for those objects on which the labels have not been printed, or on which where there are no labels, for the magnet, of course. And if the compass is not responding to that material, that means that it is not a magnet in the first place. Okay, so these are the uses of iron and steel. So iron is referred as a temporary magnet. Why do we call this a temporary magnet? Because we can easily magnetize it, demagnetize it without it storing any magnetism. But the steel has a problem, which is a blessing in disguise, but it's a problem as well. If you use steel close to a magnet, it will retain magnetism. It will start retaining magnetism. And that is how we actually make magnets artificially. We actually introduce strong magnetic fields to steel, and steel retains that magnetism, right? So I would advise you to read the slide right now. I'm taking a pause at this point. Moving on to the next part. This will be in next chapter, the uses and the transformer, right? Uh, okay, so this is an ammeter. Do you remember where we used the ammeter? We use the ammeter to measure the amount of current through any circuit, and we use a voltmeter to measure the voltage. So this is a ammeter. This is an ammeter. How does it work? Let's try to zoom into the situation. This is a part of our course, and we need to understand it. A very simple construction, but let's try to see this. Okay, so what's happening at this point is, sorry. We have deliberately made a coil at the center and try to realize that on the outer side we have two poles, north and south, right? The cylinder that is placed at the center at this point is basically an iron magnet, or it's basically iron. We're using iron over there to strengthen or to increase the strength of magnetic field because when the current passes through the core or through the wire, it prefers to pass through iron rather than air. So this is just an added bonus, you can say. Otherwise, even if it wasn't there, it wouldn't matter that much if the current is high. But only we'll have to make a lot of coils to increase the strength of the magnet. But let's see how it's working, right? Okay, so at this location, at this point, we can see that, just a minute. So what we do is that we know that the ammeter is connected like this, right, in the circuit. From one terminal, the current enters, and from the other one, the current leaves it. So when the current actually enters from one terminal, it actually revolves around this coil and then leaves the circuit. So when the current actually enters the coil also becomes an electromagnet. This is going to be the part of our next chapter. What is an electromagnet and how it is formed? So when the current actually passes through this coil, it becomes a magnet itself. Now just imagine that you have an external magnet, north and south, and you also have a magnet between them that exhibits the property of a north and south pole. So they will either be attracted or repelled because of that. And as a result of that, it will start rotating on this pivot that they've installed. And as a result, this needle will start moving to the respective value. So the higher the current, stronger will be the electromagnet between the permanent magnets, stronger will be its deflection away from the 0 point. Do we understand this idea? So that is how they are actually using an ammeter to measure the value of current. And the voltmeter is basically the same device as ammeter. The only difference is that for an ammeter we have a slight small difference that they have a shunt resistance in parallel, right? And for a voltmeter they have a series of resistance, heavy series resistance. So a very heavy resistance installed in series with an ammeter will eventually make this a voltmeter. You will read this at a higher levels, right? So ammeter and voltmeter just have a different implementation. Otherwise, the mechanical construction is 100% exactly the same. So now yeah. So then we have general day life uses of magnets and magnetic materials. So you may notice that you have door catchers with your fridge and refrigerator, and even for the deep freezer, that when you close the door, you may notice that these doors have rubber seals around them. Those rubber seals are basically not rubber, they are magnetic materials. So when you close the door, you may notice that it actually tries to grab it on its own when it's very close to it and it grabs shut. So what we've done is that the frame of the fridge is deliberately made out of iron and the strip that we installed over here is magnetic. So this is a magnetic strip which eventually, of course, brought close enough, will try to attract the iron and it will keep the door airtight or keep the door shut. This is what a speaker looks like from the inside. Now, interestingly, the speaker that we are actually using right now as headphones, hands-free, even the Bluetooth one, even the one that we use in assembly sometime, even the speaker that is used in a concert, all the speakers look like this. So how does it function? So what we've done is that we have a permanent magnet on the outside and we deliberately make a coil at the center of that magnet and bring it back. Are we familiar with the aux cable that we sometimes use with the phones that have the headphone jack, right? And the laptop as well. So this is that aux cable eventually that you plug into your laptop or phone or Game Boy or whatever you're trying to play a game on, or let's say you're watching a movie right now. So what happens is that we introduce a signal of music, sound, whatever there is, through this aux cable. When it actually runs through the coil, it makes the coil an electromagnet once again. So if this is an electromagnet and we have permanent magnet on the outer side, for example, this is north, this is south, doesn't matter. So what happens is that depending upon the value of the current, be high, low, positive or negative, the coil becomes stronger, weaker or an opposite magnet. As a result of that, let me draw this over here. So this is my permanent magnet placed on the outer side. This is a simple iron ring, and this is my external magnet on the other side. So this is north, this is south. What we have over here is that a coil installed like this around the center pivot, and then the wire is being taken back to be given to the mobile phone or to the laptop or whatever that is, right? So the coil itself, when experiences current, becomes an electromagnet. So either it's going to have a north pole or south pole at some times, either it's going to have a south pole or a north pole sometimes, depending upon the direction of the current flowing through these aux cables. So what's going to happen is that attraction and repulsion will take place between the external magnets, and as a result, the coil starts moving upwards and downwards. Now, when we receive this motion, what we're going to do that we're going to exploit this behavior, and I'm going to attach a surface or a paper surface with this cone. So if the coil moves, the paper surface will also move upwards and downwards. And if the surface or if any surface in physics moves, that produces sound. Why? Because sound is a series of compressions and rarefactions. So what happens is that when the coil moves upward, the paper cone moves upwards, pushing all the particles together in a tight fashion. So that generates a compression phase. But when the coil moves downwards, it immediately, when it moves downwards, it immediately allows these particles to have more space. So they are more spread out in that case. So that generates a rarefaction phase. And since we are sending in a signal that's varying many, many times over the course of time with positive, negative, higher, lower voltages, the coil keeps on responding accordingly. The cone keeps on moving accordingly, and eventually the respective sound is going to be produced. Do you understand how a speaker works? All other stuff that you see over here, that soft paper cone and copper coil, so copper coil is necessary, but the folding ring and the paper cone or this part of the speaker, these are all here to improve the quality of sound. They have nothing to do with the generation of sound. Our syllabus or our course deals with the generation of sound. We need to understand how it is being generated. Okay, so these are the uses of the magnets, right? One more use you may find is in scrap yards. In scrap yards, what we do, we have an electromagnet, we have a crane system, we have an operator inside it, right? And we have a crane. So what that crane does is that it has an electromagnet in it, in the centerpiece, which is a strong coil, right? And wires running through it. And the operator has a switch that it can operate to turn this or to switch on or off this electromagnet, right? So what happens is that when he switches it on, this will have a north and a south pole. So he lowers the crane, lifts up the metal scrap, gets attached to the crane, and then moves to a new position and then simply switches off. When it is going to switch it off, the coil has no current in it, the coil loses its magnetism, and eventually it will not be a magnet anymore. And if the crane is in a new location, it will drop this metal part on the lower ground. Do you understand this point? So in scrap yards, they are using this technique in some way or the other. We can also find a few more uses.